you recall, wanted to refocus this week on what integration is for and what we can do with integration. The way we think about integration is as multiplication, but one of the factors is continuously variable. So since we can frame integration as multiplication, but one of the factors is continuously variable, to find applications of integration, all we need to do is find applications of multiplication and make one or more of the factors variable. And so that's what we started doing. Yesterday, we were calculating mass by multiplying the density by the volume. We actually never got to a volume, multiplying the density by a length or an area. Density is just how much is there divided by how much space it takes up. So when everything is constant, we get to multiply. Yesterday, our first rectangle, 3x5 rectangle. These are centimeters. Our first 3x5 rectangle had a constant density of 2 grams per square centimeter. Since everything in our multiplication was constant, we got to multiply 2 times 3 times 5, 30 grams. But then we switched to a variable density. The way we play the calculus game is just take a multiplication problem. Mass is density multiplied by area, and make one or more of those factors continuously variable. So we took density and turned it into the function 1 plus 0.4x. So the density varies with distance from the y-axis. So our density was 1 plus 0.4. The length of this rectangle is 3. And the width was delta x. Density, length, width. And then this is the mass of just that slice. So the total mass is going to be the integral. We factored out the 3. And we're just integrating the density over the width. Some of the details. My discrete xi became a continuous x, and my discrete delta x became a continuous dx. And this was some number of grams. Then what we can do is we can just change another one of these factors. Vary the density, but constant length, and the width is our delta variable. The next problem that we did was we varied the density, and then we varied the length. We had the same density, but we went with a triangle instead. I think I picked this upper triangle. If the density was constant throughout this triangle, then we would just multiply area 1/2 base times height multiplied by the density of, let's say, 2, like we had in our original rectangle. And that would give us whatever that is, 15. But we have the same density, which is going to be variable. So we're going to do the same thing at a point, at this point, xi units. We're going to calculate the mass of that slice. And mass is still density times length times width. Now, if we look at that particular point xi, not only is our density going to be variable, but our length is going to be variable as well. Our density here is still but now our length is going to be variable. And we can still use the width, the delta x for the width. Now we're given an expression for the density. That's still going to be the 1 plus 0.4 xi. But now we have to write a new expression for the length. So notice that when x is equal to 0, the length is equal to 0. And when x is equal to 5, the length is increased to 3. So our length started off at 0 and increased by 3/5. Oops. Increased by 3 over 5 units. And so that was our expression for the length. Our width is still a delta x. And then we can still turn this into an integral. So our total mass, I'm going to factor out the 3/5. We're still integrating the function, we're integrating an x times 1 plus 0.4x. And delta x still becomes dx. On both of these, we have to, once we switch from adding up, in the Riemann sum, we're adding up n rectangles. In the definite integral, we're plugging in a bunch of values of x. So instead of talking about the number of rectangles as we did in the Riemann sum, we integrate, in both cases, all the x values where we have one of these rectangles. Here's what we want to look at. Here's another way to consider what's going on. This expression, what we're doing in this definite integral is we're evaluating this expression, x times the 1 plus 0.4 x times dx, at all these points as x goes from 0 to 5. So the integral part is telling you what values of x you're plugging into this expression. That's one way we want to think about how this works. So we're evaluating we're evaluating the expression x times 1 plus 0.4x times dx at all those values of x, for all the x between 0 and 5. And just adding up those values. The tricky part of the expression is all the values between 0 and 5, because there's an infinite number of values between 0 and 5. And moreover, there's an uncountable infinity of real numbers between 0 and 5. That's the difficult part. That's where we switch from a discrete sum, where the I from 1 to n counts the number of rectangles, or marks all the different rectangles, to a point where we don't have an indexable set. We can't list all the real numbers between 0 and 5. Fortunately, we have our fundamental theorem of calculus, and that's allowing us to add up those values. We can find the antiderivative, plug in the endpoints. Or we pretend that we find the antiderivative and plug in the endpoints, even on an easy one like this polynomial, by grabbing a calculating machine and having the machine do it. So here's how we want to think about integration. So let's suppose we keep the same density, the 1 plus 0.4x. Let's keep the same density, but let's change the shape. I want the same corner, but instead of connecting the 0, 3 to the 5, 0, instead of connecting that with a line, I'm going to connect with a parabola. We'll have a vertex at 0, 3. Let's put the vertex there. So now from 3 to 5, I got a vertex. I got a at 0, 3, so that's where it's flat. I'm going to bend a parabola connecting these 2 points with the vertex at 0, 3. We still want to find the mass of this bent triangle, or a triangle with bent hypotenuse. And mass is still density multiplied by length multiplied by width, density times area. Our density is given at a point xi. So I should mark that. And we'll make a note that the density at all the points where for this x value, the density is 1 plus 0.4x. Then at that point, we're going to multiply by the area, which is going to be the length and then the width will be a small piece of that area, a small change in the x. So my width is still the delta x. My density is still 1 plus 0.4x. My length is now different. My length is going to be the distance from the line down to that parabola. So if the vertex is at 0, 3, and the parabola passes through the point 5, 0, I can just grab some side work over here. The vertex form of a parabola is a times x minus h squared plus k. If I have a vertex of h, I have a vertex h and k. So if my vertex is 0, 3, then my equation looks like a times x minus 0 squared plus 3 equals y. And if I know that this parabola passes through the point 5, 0, I can plug that in for x and y and figure out what a is equal to. By plugging in the point x and y. So now I know that that parabola is y equals negative 3/25 x squared plus 3. Now that's not what I'm going to use for the length. That's just the equation for this parabola. That distance is this y, this distance. And I don't want that piece, that's open space. I want the distance from 3 down to that piece. So our length is going to be 3 minus the parabola, which we could simplify to just be 3/25 x squared. Now I've got the 3 pieces that I need to build my integral. I've got the density, which is 1 plus 0.4 xi. The length at that point will be 3/25 xi squared. And the width is where we get the delta variable. So our integral, I'm going to factor out the 3/25. and we have xi squared. Oh, x become our continuous, our discrete xi will become the continuous x, and then we multiply by 1 plus 0.4 x. Our discrete dx, delta x becomes a continuous dx. We still integrate where all the x values are, so we'll integrate from 0 to 5. Questions? Yeah. A is the leading coefficient of the parabola. I need to describe the parabola with a vertex at 0, 3, and that went through the point 5, 0. So I just wrote a generic parabola. A is leading coefficient times x minus h squared plus k. So we should evaluate this integral by hand. So we'll use our hand to grab our calculator, and we'll do 3/25 times the integral of x squared times 1 plus 0.4x with respect to x from 0 to 5. Oh, it's not 1 minus. 1 plus. What? How's everybody okay? So this is the game. I give you something with multiplication. Density is length, mass is density times area, density times length times width. And I just start making things variable. There's another thing that we can vary. Now let's vary the variable part. So let's use the same area. Let's grab the same area, the one with the parabola, but now change the density, not just to different values, not just with different values, but in a different direction. Now the density is varying with the y. The density varies vertically. Now the density is varying with y instead of x. Kept a lot of stuff the same. This is still the parabola. This parabola is still y equals negative 3/25 x squared plus 3. Mass is still density. Mass is still density. Length and width. But now, instead of density varying with x, density is a function of y. So I want to mark where the density is constant. The density is not constant at these x values anymore. The density is constant at y values. So if here is a point where the density will be constant. So I'm going to use that density for all the area at that height. And so I've got length times width. In this case, my width is going to vary with y, and my length is going to be my delta variable. So I've changed not only the density, I've changed the direction that the density is changing. So I've got an expression for the density, that's 2 minus the 0.5 y. I've got an expression for the length, that's going to be the delta y. I need to figure out what the width is in terms of that parabola and the vertical line x equals 5. So those are the changes that we made. Thinking ahead to the integral, we're integrating dy, so we don't care that x goes from 0 to 5. We care that y goes from 0 to 3. So those are the adjustments that we have to make. So our density in our mass here, the density is 2 minus 0.5 y. Our length is the delta variable. We need to come up with an expression for the width. The largest value of the width, the right side of the width is 5, and the left side of the width is the parabola. So I need to write 5 minus the parabola. The problem is the parabola is y as a function of x, I need x as a function of y. So when we go to calculate the width, I'm going to do 5 minus the parabola, which can appear as 5 minus negative 3/25 x squared plus 3, but this is not helpful. Because we need this in terms of y. So what we're going to have to do is grab our parabola fix it so x is a function of y, and plug that in, 5 minus the parabola. So let's grab our parabola. And we'll solve for, let's see, subtract 3. So negative 3/25 x squared is y minus 3. Divide by the 25, negative 25 thirds. So x squared is going to be negative 25 over 3 times y minus 3. Looks kind of bad, so why don't we write it this way? If I multiply the negative times the negative, that gives me a positive 25. Negative times positive makes negative. Now it looks more like a line. A little better. But then we have to take the square root. So we'll x equals plus or minus the square root of 25 minus 25 thirds y. Given the values of y that we're dealing with and the values of x that we're dealing with, we want the positive one. So all the x values are positive in this shape. So we're going to grab the positive square root. So our width is going to be 5 minus the positive square root of 25 minus 25 thirds y. We had to remember some algebra shenanigans while we were doing this problem. But the calculus thinking, setting this integral up, all that was the same. Mass is density times length times width. Is everybody okay? All this started with just the rectangle, 0 to 3 on the y, 0 to 5 on the x with a constant density. And we just started making things variable. Yeah. Yes, I had to go from x squared is multiplied by negative 3/25. So I'll divide both sides by negative 3/25, which means multiplying by negative 25 thirds. And then we just use the distributive property. So the other piece of this is that we have to build the integral. And so the total mass is going to be the density the length is the delta y, so I'm going to move that to the end as a dy. And then I have 5 minus the square root of 25 minus 25 thirds y times dy. That's just writing the mass of that slice, adding up all those slices, and then going to a definite integral. The last part of the problem we need to answer is what values we're plugging into this function. And here we're going to plug y, plug in the values of y where we have one of those rectangles. So y will go from 0 to 3. Then we can grab our calculating machine. It's going to be a little bit messier to plug in, but still we can just plug this in all in one go. So we're going to do the integral. F an integral. My first factor is 2 minus 0.5 y, close parentheses, open the next parentheses, which is 5 minus the square root of a bunch of stuff. When I hit square root, I open up parentheses. So I'll do 25 minus. Then I got to make sure the 25 thirds is multiplied by y. That's 25y over 3 or 25 over 3 times y. Now I'm going to close the radical, close that second set of parentheses for the red factor, comma x, comma 0, comma 3. And hopefully I typed everything in right. So it looks like 4.75. So remember that this, we're not going to be able to compare what's going on with the density here with our original, because I've changed the way the density is varying. The density in the previous problem started off at 1 and got bigger as x increased. Here, for any value of x, the density is constant. Or sorry, for any value of y, the density is constant. The density starts off at 2 and decreases by a half for every unit of y. So we're not going to be able to compare this to the 30 grams that we had before and how this parabola divides up the area. Although what might be interesting is to figure out what, if we use the same density, but go back to the original rectangle, what changes? We bring this back around and take this new density back to our original rectangle. So instead of being interrupted by this parabola, now at this particular value of y, we have our constant density. And that density is going to be for this width. And we're going to use that constant density for some small change in y. And what changes is that instead of having that weird variable width, our width is now a constant 3. So the mass of the slice, which is density, length, and width, our densities are still our same variable y density, 2 minus 0.5 y. Our length is the delta variable now. And the width is a constant 3. So instead of having this weird line minus parabola width that we had in that problem when we first switched the density, Now our density is, our width, excuse me, is a constant 3. Any questions? Notice that we've done very little calculus stuff today. All the calculus mechanics we have relegated to the machine. Just started asking the machine to do it. Even though everything was polynomials and it wouldn't be too difficult. One last one to think about that we won't be able to write very much for. So let's suppose, now I know this is single variable calculus. You sign up for single variable calculus. I shouldn't be doing this like functions of 2 variables stuff, but let's make sure that our calculus thinking is in place. So now I'm going to use the same rectangle, but instead of the density being varying with only x or only y, I'm going to make the density variable with x and y. So at different points in this rectangle, so if I pick a point here in this rectangle, that's, let's say, at xi and yj. The density at this point is some function of x and y. Mass is still density, length, and width. All my function is caught up in this density business. I got to figure out what I'm going to do to make an area. What length and width am I going to use? Because if I move the function, if I move this point a little bit off this x, then my density changes. But if I also move it up a little bit, my density changes. I can't draw a line through this rectangle where the density is constant. The density is only constant at this little tiny point. So if I just explain right now what's going to stand in for your length and width and vector area, calculus will make sense. And once you get to Calc 3, life will be easy. The teacher will just be like, oh, hey, remember calculus? More variables now. And you'll be like, oh, got it. If I explain it right now. If I wait until tomorrow, it's ruined. The effect, the magical spell will not take hold. And calculus 3 is just going to be this giant struggle. So all I have to do is explain right now what this area is going to be. What's my length and what's my width? So here it goes. How to make calculus easy in one fell swoop. Oh, shoot, we're out of time. That's going to do it for today. I'll see you all on tomorrow. Have a good day. Thanks for playing.